imagine asking an electron, where it is and where it's going. What if its answer wasn't like a precise address or some fixed path, but more like a complex drumbeat, a rhythm of possibilities? Today we're taking a deep dive into the mind of Werner Heisenberg. He lived from 1901 to 1976, a truly brilliant physicist. And he was the first to really write the language of the universe in exactly that way, rhythmic, probabilistic. Our mission here is to really explore Heisenberg's revolutionary ideas, how he stripped away those old familiar pictures, the imagined orbits and atoms, and revealed instead a world built on what we, using motion theory, call structured motion and these fundamental rhythms. We'll be using the lens of motion theory to try and really grasp the lasting impact of his work.
Yeah, and this isn't just, a history lesson about quantum physics. It's really about a fundamental shift in how we even understand reality. Heisenberg's thinking, it laid the groundwork for so much. And it still has these profound implications today for cutting-edge tech, even just how we perceive the universe. We'll try and connect those dots for you, show how these kind of abstract ideas show up in the real world. Motion theory really helps clarify those connections.
Okay, so let's dive in. Let's start with the big shakeup, the moment Heisenberg really turned classical physics on its head. Before him, you had the old quantum theory, right? Picturing electrons on these neat classical orbits like tiny planets.
Like little solar systems.
Exactly. But those models, they needed some pretty awkward patches, didn't they? Arbitrary rules just to make the math sort of fit what they saw.
They were kind of kludged together.
Then 1925, something radical happens. Heisenberg's off on this island, Helgoland, recovering from really bad allergies.
Yeah, exiled by hay fever, basically.
Right, and he has this incredible insight. He just says, look, anything we can't directly observe, like an electron's precise orbit, let's just ignore it. Let's throw it out of the theory.
That's absolutely right.
Okay.
A huge move. He focused only on what you could actually measure in experiments. Things like spectral lines. Those very specific frequencies, the colors of light and their intensities that atoms absorb and emit. They're unique light signatures, basically.
Okay.
And when Max Born, one of his colleagues, saw Heisenberg's arrays of these transition numbers, he recognized them as matrices. And that just opened up a whole new mathematical world. So with Born and Pascal Jordan, they quickly built matrix mechanics.
Right.
And in this new way of thinking, observables, things you measure like position, momentum, they become operators. Mathematical instructions, sort of.
Okay, operators.
And the way a system changes, its evolution, that's described by commutator algebra, captured in that famous equation SEIJ.
Which tells you?
Yeah, it basically describes how any measurable property A changes over time. It's driven by the total energy H and involves this thing called a commutator, HA, which measures how much those two properties, energy and A, sort of interfere with each other quantum mechanically. It was a monumental shift away from pictures to algebra.
Wow. Okay, so if we ditch the little orbiting ball picture, what does this motion-first physics actually look like, especially through that motion theory lens you mentioned? How do we think about these operators and commutators?
Well, from a motion theory perspective, yeah, the main things aren't tiny billiard balls zipping around.
Okay.
Instead, reality is about how a system can, let's say, rephase, how it can shift from one pattern of motion to another, and crucially with what strength or probability.
Rephase, like changing its rhythm.
Exactly. Think of those operators and commutators as describing the fundamental rhythms or loops a system can participate in. Structure, like an atom's energy levels, emerges not from a static thing, but as stable eigencycles.
Eigencycles, like preferred patterns.
Yeah, persistent characteristic oscillation patterns the system likes to settle into, like the pure notes of a tuning fork. It's all about loops, couplings, and their resonance rules. So Heisenberg didn't just rename stuff. He fundamentally changed the verbs of physics. Explaining something after him meant identifying these dynamic loops, writing down the commutators that describe how they interact, how the rhythms mix or interfere, and then calculating the results, like those spectral line shapes.
Okay, that's a big shift. And this leads us somewhere really interesting, maybe a bit counterintuitive for a lot of us, but absolutely crucial. Everyone's heard of Heisenberg's uncertainty principle, 1927, XONO.
The famous one.
It tells us we can't know both the precise position and the precise momentum of a quantum particle at the same time. But what's the biggest misunderstanding people have about that?
Oh, easily the biggest one is that it's just a limitation of our measurement tools.
Yeah.
Like, oh, we're just too clumsy, our instruments aren't good enough.
Right, like if we just had a better microscope.
Exactly. But Heisenberg himself, with his amazing gamma ray microscope thought experiment, showed it's way deeper than that. It's baked into reality. It's a bound of nature. His thought experiment showed that if you try to pinpoint an electron's position really accurately, say using a very short wavelength photon, like a gamma ray,
Yeah.
that very active measurement, the photon hitting the electron, gives it a kick. It injects momentum fuzz, unpredictability in its momentum through the recoil. It's not instrument sloppiness. The act of measuring one thing inherently disturbs the other.
So it's fundamental.
It is. And motion theory offers a really nice way to think about this.
Oh.
Dix and depth aren't really measures of our ignorance. Like there's a true value we just can't see.
Okay, so what are they then?
They're about how a loop distributes its phase across these complementary ways of describing it. Position and momentum are like two different facets of the same underlying rhythm. Basically, concentration in one channel demands spread in its conjugate. If you squeeze the uncertainty in position, making it really small, the uncertainty in momentum has to spread out to compensate and vice versa. Think of it like maybe a sound wave. A very short, sharp pulse, pinpointed in time, like position, inherently contains a wide spread of frequencies, like momentum. A pure single frequency needs to last a long time. You can't have both perfectly defined.
Ah, okay, that helps.
And that fundamental trade-off, that sort of minimum amount of fuzziness, is set by h bar, the quantum of action.
Yeah.
It's the smallest possible chunk by which motion can update itself. So uncertainty isn't a bug, it's a feature. It's like a conservation law of coherence. The total quantum crispness is fixed, you just redistribute it between different properties.
A conservation law of coherence. I like that. That's a great way to frame it.
Yeah.
So if it's this fundamental aspect of reality, this conserved thing, what does it let us do today? How does it show up in technology?
Oh, we see its modern echoes everywhere, especially in things like squeezed states.
Squeeze states.
Yeah, these are quantum states where scientists and engineers intentionally reduce the uncertainty in one property below the standard quantum limit, even though it means increasing the uncertainty in the other conjugate property.
So you're manipulating the uncertainty.
Exactly. You're exploiting the trade-off. A prime example is LIGO, the gravitational wave observatory.
Right, detecting ripples in space-time.
They use squeezed light. By squeezing the uncertainty in one aspect of the laser light they use, they can dramatically reduce the noise in measuring the positions of their mirrors.
Making them super sensitive.
Super sensitive. Sensitive enough to pick up those tiny gravitational waves from colliding black holes billions of light years away. Even though the momentum uncertainty of the light goes up, they don't care about that as much for their measurement. It's pure Heisenberg, but used as an engineering tool. You remix the coherence budget for what you need.
That's amazing, taking a fundamental limit and turning it into an advantage. Okay, let's dig into this a bit more. If we can't know everything at once, if there are always these trade-offs, how do we actually get reliable information about the quantum world? Niels Bohr talked about complementarity, this idea of mutually exclusive views, but Heisenberg really made it operational, right? Tied it to the actual measurement process.
He did. What complementarity means, practically, is that quantum descriptions require mutually exclusive measurement arrangements.
Meaning you have to choose what you measure.
Precisely. You can't set up one single experiment that shows you all the quantum features, like both waves and particle aspects, or exact position and momentum simultaneously. You have to choose. You set up your apparatus to measure position, and you get position information, but you inherently lose the momentum information in that process, or vice versa. The choice of how you measure dictates what facet of the quantum rhythm you interact with and observe. The observer isn't passive.
Okay.
And Heisenberg also really emphasized what he called the Heisenberg cut, this crucial conceptual dividing line.
The cut.
Yeah, the idea that you have to treat the measurement apparatus itself, the thing you're using to measure, as classical, while the system you are measuring is treated as quantum.
Why is that so important?
Because to make any sense of the quantum results, to make predictions, you need stable reference rhythms. You need a reliable, predictable, classical background, our clocks, our detectors, to compare the quantum phenomena against. If your measuring device was also fully quantum and unpredictable in the same way, you'd just have quantum fuzz measuring quantum fuzz, an infinite regress. You need that classical anchor point.
That makes sense. You need a stable ruler to measure something wiggly. What's fascinating here, though, is how motion theory provides a, well, maybe more intuitive picture of this measurement process.
I think it does. Motion theory translates measurement not as just passively looking, but as an active process of synchronization.
Synchronization.
Between the microscopic quantum loop, the system you're measuring, and the macroscopic timing network, which is basically our classical measurement apparatus. You can't really read the phase, get the information from a quantum rhythm without somehow joining it, engaging with it.
Like you can't understand a dance just by watching. You have to sort of feel the beat.
Exactly like that. You have to interact, synchronize, even momentarily, to extract information. So it's not passive observation. Every measurement is a duet. It's this active interaction where the observer and the observed system briefly lock into a shared rhythm, and that interaction produces the measurement outcome we see.
A duet. I really like that metaphor. Okay, moving on to another big challenge Heisenberg took on. How do you even describe something super complex like a particle collision if you can't visualize the paths the particles take during the smash-up? This was a big issue.
Huge issue. And in the 1940s, Heisenberg came up with a really ingenious solution. He basically said, let's stop worrying about picturing exactly what happens during the collision in that messy interaction zone where our classical intuition breaks down anyway. Let's focus only on the in-out states. What particles go in long before the collision and what particles come out long after it's over.
So just the before and after.
Exactly. And the mathematical tool that connects the in state to the out state is the S matrix, the scattering matrix. This trajectory-free approach was incredibly radical. It completely abandoned trying to visualize paths in the middle, but it turned out to be incredibly powerful. It blossomed later thanks to people like Wheeler, Dyson, Chu, and it still forms the absolute foundation of how we analyze experiments at particle colliders like the LHC today. It lets us calculate probabilities for outcomes without needing that impossible-to-get microscopic picture.
So no paths needed. How does motion theory then describe this trajectory-free idea? It feels so alien to our everyday experience of, things moving from A to B.
Well, think of a collision less like tiny balls bouncing off each other and more like coherence plumbing.
Coherence plumbing.
Imagine far away from the interaction, you have these well-defined motion loops. Those are your incoming free particles. Stable rhythms like smooth water flow.
Right.
But near the collision point, these loops get complicated. They mix, they entangle like water swirling through a complex junction of pipes and valves.
At a chaotic mess in the middle.
Potentially, yeah. And then out the other side come new, stable rhythms. Those are your outgoing particles. The S matrix, in this view, is essentially the transfer function of that plumbing junction, that mixer. It tells you, given these input rhythms, what output rhythms are likely to emerge. It captures the net effect of the mixing process without needing to detail every twist and turn inside. So one of our motion theory one-liners for this is, an S matrix is a mixer. Input rhythms, output rhythms, no path required. You just care about the transformation.
Input rhythms, output rhythms. That's a neat way to think about it. Now, Heisenberg's insights, they weren't just about single particles or collisions, were they? They also helped explain how matter itself gets organized on a larger scale.
Oh, absolutely. He made fundamental contributions to understanding collective phenomena. For instance, he provided the first real quantum explanation for ferromagnetism, why materials like iron become magnets. This was with his idea of the Heisenberg exchange interaction in 1928.
Exchange interaction.
Yeah, it's a purely quantum effect. It describes how the spins of neighboring electron spin is like a tiny intrinsic magnetic moment, tend to prefer aligning either parallel or sometimes anti-parallel to each other. This preference arises from quantum symmetry principles, specifically how electrons, being identical particles, behave. It has no classical counterpart.
Okay.
And this interaction leads directly to the Heisenberg model, which is still a cornerstone for understanding magnetism and lots of other many-body quantum systems today. From the motion theory perspective, you can picture a ferromagnet as a lattice, a grid of these local spin loops. And these loops phase lock with their neighbors through this short-range exchange coupling. The alignment spreads. Long-range magnetic order emerges as coherence percolation.
Like a wave spreading through a crowd.
Exactly. It's like a stadium wave of spin alignment. So ferromagnets that are phase-locking cascades of spin loops. The alignment propagates, creating the bulk magnetic property.
Cool. And he had other ideas about internal properties too, right? Like isospin.
Yes, isospin, which he introduced around 1932. This is a way of thinking about the proton and the neutron.
Which are very similar in mass.
Very similar, yeah. He proposed viewing them not as fundamentally different particles, but as two different states of a single entity, the nucleon. And you could transform one into the other through a kind of rotation in an abstract internal space. This internal symmetry is described mathematically by SU2, similar to how we describe rotations in regular space.
So like different orientations of the same thing?
Sort of. Motion theory sees this as a kind of hidden orientation in an internal motion space. Interactions, particularly the strong nuclear force, care about the relative phase or orientation in this internal space, not just whether it's a proton or neutron label. It's like two variations on the same fundamental rhythm.
This idea of internal spaces and symmetries is huge in modern physics. Now, this raises another big question that physicists grappled with, especially back then. Those pesky infinities that kept popping up in quantum calculations. Did Heisenberg have thoughts on that?
He did. He definitely wrestled with the infinities that plagued early quantum field theory,
Yep.
and he flirted with a fundamental link.
A minimum distance.
Yeah, the idea that maybe space and time aren't infinitely divisible. Maybe there's a smallest possible scale, and below that, our current theories, our current description of motion just breaks down. This is kind of proto-effective field theory instinct, the idea that our theories are only valid down to certain scales.
And how does motion theory view that?
It fits nicely. It suggests that physics is scale-structured motion. As you zoom in or out, you encounter different kinds of loops, different rhythms, different effective laws. New phenomena emerge at different scales, and it connects back to order. Order is shared phase. The way phase coherence organizes might be fundamentally different at extremely tiny scales, perhaps taming those infinities naturally if there's a minimum wavelength or loop size.
Interesting. So beyond the pure physics, the equations and theories, Heisenberg's life had this really complex, very human dimension, particularly during World War II. It's something that's still debated quite a bit.
It is. He was a leading figure in the German Uranium Project. Their effort, however disorganized, to explore nuclear energy and potentially weapons during the war. His exact role, his motivations, his technical understanding, these are all subjects of intense historical debate. The farm hall transcripts.
Right, those secret recordings of the German scientists detained in England after the war.
Exactly. They reveal a complex picture, full of what seem like technical misapprehensions, maybe about how to build a bomb, and certainly moral ambiguity. Did he not know how, or did he deliberately hold back? We still argue about it. What's clear is that after the war, he played a really active role in rebuilding German science. He advocated strongly for peaceful uses of nuclear energy and helped reestablish international scientific ties.
It's a complicated legacy. So looking at this through the motion theory lens, beyond the physics itself, what's the lesson here about science and responsibility?
Well, for the culture we try to foster with motion theory, the lesson seems pretty stark. Precision without ethics is incomplete motion.
Incomplete motion.
Yeah. The loops of scientific discovery, however intricate and powerful, they don't exist in a vacuum. They're always embedded within the larger loops of human society, ethics, values. The point is, the loops we build should stabilize life, not threaten it.
It's a powerful reminder, isn't it? That even the most profound scientific insights carry heavy ethical weight. The coherence of our science needs to be matched by a coherence of purpose. That's very well put. A crucial reminder. Okay, let's pull back to the science. It's so clear that Heisenberg fundamentally changed the language of physics, from pictures to rhythms. So, zooming forward to today, what does this new way of thinking actually enable? How are his ideas still driving science and tech?
Oh, his legacy is immense and ongoing. His work directly underpins the entire field of quantum metrology, the science of making ultra-precise measurements using quantum effects.
Like LIGO again?
Absolutely LIGO, with its squeezed states. But also things like atomic clocks, the most precise timekeepers we have, and atomic interferometers used for incredibly sensitive gravity measurements or navigation systems. Their ultimate performance is fundamentally limited by the Heisenberg bound, by that uncertainty principle. And progress comes from clever ways engineers find to squeeze and rephase quantum states, manipulating that coherence budget he first described.
So we're actively engineering with uncertainty.
We are. We also see many-body coherence directly explored using his ideas. For example, scientists can now build programmable quantum simulators.
Using things like trapped ions or cold atoms.
Exactly, and they can actually program Heisenberg models onto these simulators and directly watch how order emerges from the quantum interactions, how those phase-locking cascades happen in real time, simulating complex materials.
Wow, actually seeing it happen.
Yeah, incredible. In high-energy physics, too, that S-matrix idea, thinking of scattering as information flow, is absolutely central. Today, S-matrix amplitudes are organized using deep principles like unitarity, making sure probabilities add up to one in fundamental symmetries. Researchers are analyzing collision debris by looking at coherence transport, how quantum information flows through the interaction.
Still using his core ideas.
Definitely.
Yeah.
And then there's something perhaps more subtle, time as counted motion. Heisenberg's equations, his uncertainty relations, they are fundamental to the very definition and measurement of time in clocks. This even extends into fields like chronotherapy in medicine.
Chronotherapy.
Yeah, timing medical treatments to align with the body's natural circadian rhythms. It's about achieving phase alignment between our internal biological clocks and the external treatment schedule, using precise timing derived from quantum-based clocks to maximize effectiveness. It's another echo of synchronization.
It really feels like Heisenberg didn't just find limits. He invented this whole new operating system for reality, this language of rhythms that's still powering innovation everywhere.
Okay, to really crystallize this, let's try and distill Heisenberg's impact into, say, 5 key punchlines from the perspective of motion theory. Insights that capture his revolutionary spirit.
Okay, 5 punchlines. Let's see. First, observable picture. What's real in quantum mechanics is what couples and clicks, what you can interact with and measure. Not necessarily something you can draw a simple classical picture of, like a little planet. Reality is the interaction, the event.
Right. Ditch the naive pictures.
Second, every measurement is a duet. You don't just passively watch, you get a value, you learn something by joining the system's rhythm, by synchronizing with it. Measurement is an interaction. The duet. I like that one.
Third, coherence isn't free. There's a fundamental budget. If you sharpen your knowledge of one aspect, like position, its complementary partner, momentum, pays the bill by becoming fuzzier. It's a trade-off, a conservation law.
The coherence budget. Got it.
Fourth, order is shared phase. Think about magnets, superfluids, lasers, all these amazing collective phenomena. Their order emerges from alignment spreading, from individual quantum rhythms locking together across the system, until something disrupts that shared phase. Order is emergent synchronization.
Order from rhythm.
And finally, fifth, the right variables are rhythms. In the quantum world, the fundamental tools for describing what can happen aren't necessarily simple coordinates like x, y, z. It's the operators and their commutators, these mathematical objects that describe the possible transitions, the allowed dance steps, the fundamental rhythms and how they relate. They tell you what's possible.
Those are powerful. Observable isn't picture. Measurement is a duet. Coherence isn't free. Order is shared phase. And the right variables are rhythms. That really encapsulates a different way of seeing things.
Yeah.
These aren't just, clever phrases. They point to a massive shift in how we even approach understanding the physical world, moving from static things to dynamic processes to rhythm and interaction.
Exactly. And Heisenberg himself argued this eloquently. He said quantum theory doesn't get rid of reality, it just redirects our understanding of it. Those classical pictures we rely on, a solid table, a definite trajectory, they're really just macroscopic summaries. They're what emerge when countless underlying quantum loops happen to synchronize on a large scale. But down at the small scales, those fundamental loops don't always align neatly to give one simple story. We have to choose which complementary aspect to look at, which measurement arrangement to use, and accept the inherent trade-offs that come with that choice.
So wrapping this up, what does this all mean for you, the listener, maybe as you go about your day after hearing this?
Well, motion theory fully embraces this viewpoint. Our picture is that the world loops plus synchronization plus leakage. It's dynamic, it's rhythmic. And maybe the real miracle isn't that we can know everything with perfect certainty. Maybe the miracle is that stable patterns exist at all within this incredible complexity, that synchronization happens, that coherence can persist, even if only temporarily or partially.
So here's something for you to maybe think about long after this deep dive is over. If our fundamental understanding of reality is shifting towards rhythms, towards synchronization, towards the inherent trade-offs of coherence, where else in your own life could you start looking for patterns, connections, and maybe the costs of focusing on one aspect over another instead of just looking for fixed positions or states? What are the stable patterns around you? Maybe in your habits, your work, your relationships, even your environment. What makes them hold together? What keeps their rhythms synchronized? And maybe just as importantly, what causes them to break down, to lose coherence, to let go?